Now let's look at finding the angle between two vectors. We now have two ways to calculate the dot product of two vectors. On the first slide, we defined that the dot product of two vectors was just the sum of the product of each one of the components. And then in the last slide, we said that the dot product has something to do with the angle between the vectors. And we said that that proof comes from the law of cosines. If we solve the last equation for cosine theta, we'll get a way to find the angle between the two vectors. In other words, if I take this last equation and I try to isolate cosine of theta, I find that the cosine of theta is equal to the dot product of the two vectors divided by the magnitude of the first vector times the magnitude of the second vector. And this is what we call the angle between vectors theorem. If u and v are two non-zero vectors, then the angle theta, where theta is between 0 and pi, between those two vectors is determined by the formula that I just wrote above. So I'll write that one more time. It's good practice for you to write it again. It's one of those things that the more you write it, the more it gets into your brain. So let's take a look at an example. Find the angle theta between the vector u and the vector v. U is defined as 2i plus 3j, and vector v is defined as 4i minus j. Part 1 says to draw a sketch of the two vectors in order to see angle theta. All right, so I'm going to start with vector u, and I'm going to put it in blue. Starting at the origin, if I move 2 to the right and 3 up, it puts me at the ordered pair 2, 3. So that's vector u. That's in blue. And in red, I'll go ahead and put vector v. Vector v is 4i minus j. So I'm going to go 4 to the right and 1 down from the origin. And I'll connect. So there is vector v. And so what I'm interested in finding on part B is the angle between those two vectors. What is that space? And we're being asked to do this by the angle between vectors theorem. So let's just write that theorem again. I know we've written it a few times, but let's just go ahead and do it. It says that the cosine of theta is equal to the dot product of the two vectors divided by the magnitude, the product of the magnitude. So in order to do this problem, the first thing I have to do is to find the magnitude, or excuse me, to find the dot product of u and v. So I'm going to say that that is equal to 2 times 4 plus 3 times negative 1. And that is equal to 8 minus 3, or 5. In my denominator, I need to find what the magnitude of each one of these vectors is. And remember that we can find the magnitude of a vector by using the Pythagorean theorem. If we know the components, which we do, then we can just put in this example, 2 squared plus 3 squared, which is 4 plus 9, so square root of 13. And then the magnitude of the v vector is going to be 4 squared plus negative 1 squared, or 16 plus 1, which is 17, square root of 17. So in my denominator, I'm going to have the square root of 13 times the square root of 17, and the square root of 13 times the square root of 17, I'm just going to leave that alone. Different radicands, so I can't do anything with it. So I wrote too big. Let me just move that denominator right there. All right. Now, let me clear the screen so that I can actually go about the business of finding the angle. Or actually, I don't want to lose this, so let me just write underneath here. I'm now going to say, let me just write here, that theta is going to equal cosine inverse of 5 over root 13 times root 17. And I'll put that into my calculator, and in degrees, my calculator is going to tell me 70.3 degrees. And does 70.3 degrees seem reasonable? It does look like it's less than 90 degrees, so I'm going to say yes, that feels reasonable. Now, one of the things on part B it says is to confirm that your answer is reasonable. So we've looked at it, but I want you to think about this for a second, and you don't necessarily have to do it now, but I would urge you to do it on your own. Without knowing the angle between vectors theorem, would it be possible, if we didn't know that, would we be able to find that angle theta? And I think the answer is yes. Now let me give you a hint here. If I look at vector u, which is in blue, and I drop a perpendicular, I've just formed a right triangle. And in that right triangle, I could find this corner angle. Let me call it maybe alpha. And in the red vector, which is v, again, if I drop a perpendicular, I have formed a right triangle. And in the left corner, I have angle beta. So if I can find alpha and I can find beta, then alpha plus beta should also equal theta. Do that one on your own, and if you have done it correctly, you should end up with the 70.3 degrees. So now that we've done all of that, let's talk about the significance of the dot product. And the first thing we're going to look at are parallel vectors. So what does the dot product tell us about these vectors? Well, the angle between the vectors gives us a measure of how well the vectors are aligned. If two vectors point in the same direction, then the angle between them would be 0. And if two vectors point in the opposite direction, then the angle between them is pi. In either case, the vectors are parallel. We can also say that two vectors are parallel if there's a non-zero scalar, alpha, such that vector v is equal to alpha times w. So let's look at example 3. Determine if the vectors v and w are parallel. And we'll start out by drawing a sketch of the two vectors so that we can see angle theta. So vector v is defined as 4i minus 8j. So starting at the origin, I'm going to go 4 to the right, and then I'm going to go down 8, and it puts me right in the 4th quadrant. And then vector w is negative 2i plus 4j, so I'm going to go 2 to the left and up 1, 2, 3, and 4. And this vector that's in red in the 2nd quadrant is vector w. Now, these two vectors may not look parallel, but you need to remember the important thing about vectors is that these vectors can be picked up and moved anywhere and retain their value. They retain their value as long as they stay the same length and they have the same direction. So in other words, this vector that's in red, I could pick up and I could move it to a location maybe in the 3rd quadrant, and as long as the horizontal distance is 2 and the vertical distance is 4, so for example, let's just say that I started it right at negative 6. As long as I start it right there, if I go to the left 2 and up 1, 2, 3, 4, that vector that's in orange is going to be equivalent to the vector that's in W. So I think now you can see that, oh yeah, they are parallel. They didn't look parallel before, but they are, simply because we can move them around. So part B says, okay, find theta using the angle between vectors theorem. Now I'm going to cross out vector that was in orange because we are working with the blue vector and the red vector. And so what we first need to do is, of course, find the dot product. So what is the dot product of V and W? That's going to be whatever 4 times -2 is, plus -8 times 4, or -8 plus -32, which is -40. And then we need to find the magnitude of each one of the pieces. So the magnitude of vector V is 4 squared plus -8 squared, 16 plus 64, which is 80. And the magnitude of vector W is going to be the square root of -2 squared plus 4 squared, which is, I think, 20. All right. So now we're going to say that the cosine of theta is equal to the dot product over the product of the two magnitudes. So if I put that into my calculator, I end up with a theta that is equal to pi. In other words, the angle between these two vectors is 180 degrees, or if we're in radians, pi. And sure enough, that's what it looks like. The last part says to rewrite vector V in terms of vector W to show that these vectors are different only by a scalar. So let's see here. Vector V, how do I get vector V to look like vector W? Well, the first component in vector V is 4, and the first component in vector W is -2. So what it looks like is if I take the scalar -2 and I multiply it by vector W, I do end up with vector V. And so let's just double check that. -2 times the first part of vector W, so -2 times -2 is 4, that checks. And -2 times +4 is -8, and so that checks. In other words, the only difference between vector V and vector W is the length, and in this case, the direction. Therefore, they are parallel. All right, and now let's talk about the significance of the dot product, not in terms of parallel vectors, but in terms of what we call orthogonal vectors. If two vectors form a right angle, then the angle is pi over 2, or 90 degrees. In this case, the vectors are perpendicular or orthogonal. In other words, those two words are interchangeable. Use the angle between vectors theorem to discover the relationship between the dot product of the vectors V and W. All right, so we start out with the angle between vectors theorem. And if we know that the angle is 90 degrees, then we have the cosine of 90 degrees. And the cosine of 90 degrees we know is 0. And if I multiply both sides by the denominator, in other words, multiply both sides by the magnitude of V times the magnitude of W, then I get rid of my denominator on the right, and of course 0 times vectors just gives me 0, and so I find out a really nice definition that says two vectors are going to be perpendicular or orthogonal if their dot product is equal to 0. So to summarize that, two vectors V and W are orthogonal if and only if their dot product is 0. So let's take a look at an example. Example 4, determine if the vectors V, which is defined as I minus j, and W, which is I plus j, are orthogonal. Now we'll start by drawing a picture just so we can get an eyeball picture of this to see do they look like they're orthogonal. So vector v I'll do in blue, and it looks like my components are 1 and -1. So that's going to be real tight on this picture, but it's going to look something like that. And then for vector w, it's I plus j, so it's +1 and +1, and so I'm going to be doing something like this, and let me actually just go over that in red. And so we are talking about, I need to blow up that graph, don't I? We're talking about the angle inside of there, and it certainly does look like it's a 90-degree angle. But we're going to go ahead and check it, because what we know is that if it really is, then vector v and vector w, the dot product should be 0. All right, so I'm going to take my A components, the first components, so 1 times 1, and I'm going to add that to -1 times +1, which gets me 1 minus 1, which is 0. So sure enough, it looks like these are orthogonal. Example 5 says to determine if the vectors 2i minus 3j and w equals -6i minus 4j are orthogonal. I'm going to clear my screen so that I can graph these new vectors. 2i minus 3j I'll do in blue. So 2 to the right, and then I'm going to go down 1, 2, and 3, and there is that vector. And then in red, I'll do vector w, 6 to the left, and 4 down. And again, it does look as though it's forming a 90-degree angle, but I'm going to just double check by finding the dot product. So I'm going to have 2 times -6 plus -3 times -4, -12 plus 12, which equals 0. And sure enough, we have perpendicular vectors.